exactly math.
That's what
Math
math
exclusively with math function.
Yes.
You make math though to make it exclusively to figure out prime numbers.
Prime numbers, that would be a good way to do math club. Yeah, we need to do something with math clubs.
Actually,
We should.
People keep asking me, what's going on with math club? And I said, nobody's in charge.
Let's meet Friday.
Friday?
Fridays.
Friday mornings at 6:30?
Ooh.
All right, we are talking about section 13.3, part 2.
Yeah, you have to wear all the French coat.
What did I just see?
I just put higher.
So we're going to talk about higher order partial derivatives. So we know how to take a partial derivative now. We take the derivative of our function with respect to one variable, but while we hold the other variable constant. We apply the same idea to second order partials, third order partials, but we have some different possibilities because we can take a second partial with respect to x or a second partial with respect to y. So a function of x and y will have a first partial derivative with respect to x and y, and then it will have second partial derivatives with respect to x and y of each of those, and so on, depending on how many derivatives you want to take. So if we start with our function, z is some function of x and y. For our higher order partial derivatives, we have 4 possibilities. So our first one, we're going to take the partial, and I'm going to write our different notation. We're going to take the partial of x, and then we're going to take the derivative of that with respect to x. The other way we write that is f sub xx. If we use our new symbol, this is d dx of df dx. And we also write this as d squared f dx squared. So all of 4 of these notations mean the same thing. We're taking the first partial with respect to x, and then we're taking the partial derivative of that function with respect to x. Our second possibility, what we call a mixed partial. So we're going to take the partial with respect to x, and then the partial with respect to y. We write that f xy. This is d dy of the partial with respect to x. And we write that as d squared f dy dx. So notice when we use the d symbols notice the order in the denominator is opposite the order that we use here. So this is telling us that we're taking the partial with respect to x first, and then the partial with respect to y. So it's related to this notation. Which one?
Like the second column.
This one?
Yeah, is it like on the same, like, on the we would write f and x, y together, or
They're subscripts.
Are we all subscripts going down?
Or no, it's
No.
like f sub x sub y. Or
No, it's
f
just
sub x, y.
f sub xy.
Okay.
So the x and y are on the same level of subscript.
So you can't do f sub x squared. You have to do f sub x sub x. Which one?
This one?
Yeah.
No, they don't use that notation. I don't know why. Right. Our third possibility is the mixed partial in the opposite order. So we're taking the partial with respect to y, and then the partial of that with respect to x. And this equals partial with respect to x of df dy, and we write d squared f dx dy. So for our mixed partials, it's important to remember the difference, what this order means and what this order means. This we read from, in this notation we read from left to right. In this notation we read from right to left for our order of our derivatives. And then our fourth possibility is just the partial of y, and then we're taking the partial of that with respect to y. So those are our four possibilities for second partial derivatives, and we can continue with the same kind of notation, same order, same kind of thinking for third order partials or fourth partials or fifth partials.
One of those possibilities is one more possibility.
Right. So there's lots. When you start doing higher order partial derivatives, there's lots of other, lot more possibilities. So we call 2 and 3, we call set 2 and 3 we call these the mixed partials. And that just means we're taking the partial derivative with respect to one variable and then with respect to another variable. So questions on the notation, questions on what we're doing? We're using the same procedure, just doing it again, basically. Now, in advanced calculus, we don't have the tools really yet to do it. We can prove that if the mixed partials are continuous, that they're equal. We're going to usually be working with nice functions that are well behaved, that are going to have continuous second order partial derivatives. So we're just going to state this as a theorem. We don't have the tools to prove it. But we're going to say that for a function, f of xy, such that our mixed partials are continuous, and they're continuous on some open disk. So there's some place, some area in some open disk where they're continuous. So there's some place where they're continuous. Then our second partials are equal.
Only on the open disk or
For just in the open disk. Every point in R. So if our partials, our mixed partials are continuous everywhere, then the mixed partials are going to be equal everywhere. But if we have to constrain it somewhere, if they're discontinuous outside of some region, then they would only be equal inside that region.
What is a mixed partial? Like the derivative of a regular function is like the slope.
Right.
So what would be a mixed partial derivative?
So if we think of our mixed, we thought of our partial derivative yesterday as we're holding one variable constant and finding the slope of the curve along that constant variable.
So it'd be the slope of both.
The slope. So what's that?
Would be the concavity.
It's sort of like the concavity. So the other day we looked at the graphs of the surface and then the graphs of the partial derivatives. So the graph of the partial derivatives were surfaces also. So then we're just looking at how the slope of that surface changes with respect to the other variable. A physical interpretation really depends on what you're interpreting your function.
Okay.
Your function. Okay. So, and this theorem is going to hold for functions of 3 or more variables as well, as long as the second partials are continuous. Then the third mixed partials are going to be equal. If our third mixed partials are continuous, then our fourth mixed partials are going to be equal as well. So we have a well-behaved function. The mixed partials.
And it seems like it's mixed partials, so like the order doesn't matter. It's gonna be
Right. The mixed partials are
Y,
equal
Y,
if your
X.
function. Essentially, what we're saying is the mixed partials are equal if your function is well behaved. Is our bottom line. So let's just do a couple of quick examples, and then we'll be done for today. So what I want to do is, let's say we have z equals x to the fourth minus 3x squared y squared plus y to the fourth. All right, what I want you guys to do, I want you guys to find the 4 second partial derivatives. And use shorthand when we're talking about partial derivatives. Instead of saying second partial derivatives, we can say second partials. So find the 4 second partials. All right, so I want you guys to come up with them, and then we'll compare answers. All right, so let's see. Let's start off. So the first thing we have to do is find our first partial. So what did the z, the x, come out to be? 4x cubed.
Minus 6y squared.
6, and I'm going to write it just x, y squared. And then our partial of z with respect to y, what does that come out to be? 4y cubed minus 6, there we go, x squared y. All right, did everybody get that for your first partials? And then we can go for our second partials. So let's look at z sub x, partial of z with respect to x, second partial of z with respect to x, what does that come out to be? 12x squared minus 6y squared. Okay. How about z, the second partial with respect to y? 12y squared minus 6x squared. How about the first mixed partial, z x y, and I'm going to write the other notation. This is d dy of dz dx. So what's that come out to be? Minus 12xy and zyx, which is dx of dz dy. And when we calculate that out, what do we see? Minus 12xy. So we have a nice, well-behaved function, and our mixed partials are equal. And we could do the same thing for higher order if we wanted to look at third mixed partials or fourth mixed partials. You just have to go through this process of finding your partials and then comparing. So any questions on the process? We're good on the process.
There should be a y on the dyx.
Z,
I think it's just a negative x.
no, yeah, I got this for. So if this is our first, if we take the partial of this with respect to y. Okay, you're good. Figured it out. Okay, good. All right. So I have a couple of thinking questions, not calculating questions, and then we'll be done. And some true or false. I like true or false for these things. All right, so for this example, we're going to say that n equals the number of applicants to a university. P is the dollars for food and housing. And T is tuition. So we're going to say that n is a function of P and T. So we're going to say n equals some function of P and T. And we know for this function that dn, the partial of n with respect to P, is less than 0, and dn dt with respect to tuition is less than 0. What does this tell us?
Increases, depending on what, as tuition increases or, the room and board payment increase, there are more applicants.
Less applicants, right?
Oh, they're less than 0.
Because they're less than 0.
Yeah, I
So,
know.
so as the price goes up, as the tuition goes up, we have less applicants because the derivative is negative. And as the cost for food and housing goes up, our derivative is negative. So this tells us that less people apply when the cost goes up. All right. I have a few true or false questions. Number 1, if z equals some f function of x and y. Here you go, Andy. I have a new one here. That counter right there is going to be really sanitary. So here's our function, and we know that dz dx equals dz dy. So our partial derivatives are equal, then z equals some constant times x plus y. True or false? Yes. So if you think it's true or false, you need to provide an explanation. Who says false? False? So what would be, you have a counter example? Well, if I took the partial of this z with respect to x, I would get c, and then when I take the partial with respect to y, I get c, right?
Second one.
Yes. There you go. So this does work for this function. Are there functions that this would be true for that are not in this form? Z equals what?
C.
C. Z equals a constant. The partials of this the first partials are 0 for both of them, right? So this would be false. So we found a counterexample, so this would be false. And we could think of all kinds of examples. The example I thought of was z equals x plus y plus 1. It's not in this form, but the first partials are equal. So similar idea. All right, second true or false question. Number 2. If z equals f of x times g of y, then dz dx plus dz dy equals f prime x, I'm going to write this on a different line, equals f prime x g of y plus f of x times g prime of y. We want to know if this is true or false.
True.
So Sean says true. What makes you think it's true, Sean?
Because if you take the derivative with respect to x, you get f prime x gy.
Right? If you take the derivative with respect to x, g of y is a function of y, so it's just going to be a constant, so you just get f prime of x times g of y.
And then if you take it with respect to y, you get f times plus
Right.
g times.
So if we take our partial with respect to y, f of x is a constant with respect to y, so we get that constant times g prime of y. So this would be true. Number 3, third true or false. If, and you might need to calculate on this one, if z equals e to the xy, then d squared z dy dx equals xy plus 1 times e to the xy. So basically for this one, find this mixed partial and see if it's equal to this. And then tell me if it's true or false. Anybody have it?
Yeah, it's true.
So we're calculating, we're saying it's true. So dz dx, or sorry, yes, dz dx, that's what we do first. Turns out to be y e to the xy. And then if we take the derivative of that, d dy of y e to the xy does indeed come out to be xy plus 1 times e to the xy. So this is true. All right, I think that's the last question that I'm going to ask today. Any questions on higher order partial derivatives? Okay, let me put your homework up here, but I have an option before you guys start working. Where are we? We are on block day. 9:12. All right, there's your homework.